Okay, I think we're rolling. Let's see. Hello, everyone. Thanks for joining. John here, staff software engineer with 10 plus years of experience. I'm the lead maintainer of Latterly.io. Latterly is a free and open source website that helps you land your first or next programming role. And today we're doing some Leetcode. So here's Latterly.io. You can go sign up for free and you can upgrade optionally for some advanced features. If you go to the blog article number 3 is the Leetcode kata, and then solutions are in article 7. And that's what we're doing today. We're practicing some Leetcode. So this is the Leetcode kata. We're going to do clone graph number 133. I haven't done this problem in a while, so we will do a time check at the 20-minute mark. I'm going to do I do a 20-minute time box on problems anyway. If I solve it in under 20 minutes, I may continue to course schedule. But if it takes me more than 20 minutes, then we'll save course schedule for another video. So hope that makes sense, the format of how we're proceeding. Why am I doing Leetcode? I set out a poll, and earlier this week it was 50-50, so I planned on doing one of each. Now it's 2/3 for open source. I will be doing one of each. Hope you'll follow the page. After this stream, I will be doing some open source work. And so if you would like to influence the types of videos that I make, head over to the YouTube channel. Link will be in my bio if you're not on YouTube already. And occasionally I send out polls like these. Also, I sometimes send them out on my LinkedIn as well. Or you can just shoot me a DM or drop a comment, whatever you think's interesting. Okay, so here's clone graph. We'll start by reading the problem. Given a reference of a node in a connected and undirected graph, let's return a deep copy or a clone of the graph. Each node contains a value and a list of its neighbors. A list of its neighbors. Okay, so for simplicity, each node's value is the same as the node's index. Okay, that's interesting. An adjacency list is a collection of unordered lists used to represent a finite graph. Each describes the set of neighbors. And Leetcode gives us this commented class for node, and we can see neighbors, if neighbors is not none, else an empty list. So neighbors can be none. It's nullable. None is the Python word for null, basically. So neighbors will be none or an adjacency list. And then here's an example. We have a graph. We don't want to return the same graph. They need to be in order 1, 2, 3, 4, right? Okay. So notice that this is a perfect square, so that if I did some sort of loop, there's a dangerous case where 1, 2, 3, 4 connects back to 1, and I get into a cycle, an infinite loop. So I need to be careful to avoid that. Example 2. I'll return an empty list of lists. That's interesting. So what is the difference between example 2 and 3? The input contains one empty list. So I'm noticing that the node argument to clone graph is optional. So I think that example 3 is referring to the case where even the head node is null. I think that's what's going on. And so I think this means that we should just return null or none. I think this is like a strange syntax. We'll test it, but I actually suspect Leetcode does not want us to give a literal empty list in that case. But we'll test it. So I'll just handle this edge case before I really think about the different patterns that I'm going to do. But I'll say if not node, return none. And then I'll put it to do here just so I can remember. Okay, so forgetting about this edge case, we'll have some sort of loop. Whatever loop we have, I'm pretty sure this will be rolled in. So I don't know that we need to specially deal with example 2, except to note the fact that neighbors can be none. So we shouldn't assume a list. I think that's my main takeaway from example 2. So most of the meat and potatoes is here in example 1. So we're given value 1. We're given them in order, right? So 1 is going to point to 2, and then 3, 4, and so on. And our traversal patterns typically include DFS and BFS. So let's imagine DFS. Often it's easier, like more concise to write out. And in addition, I am going to want to do some sort of caching to avoid a loop. And DFS with caching is pretty common, fairly straightforward pattern. Although you can cache in BFS as well. It's just a bit more verbose if I'm picturing them properly in my mind. So given that I have 1, I'll have some function. Maybe it's a helper function, or maybe I can call clone graph itself. And I will call that on each neighbor. So in this case, 1 only has a single value in the list of neighbors. What if it had 5 who was parallel to 2? So imagine that this is like 3D. And 1 branches to 2, and then 1 branches out to 5. And there's like another square over there. So then the shape of the whole graph is kind of like a greeting card in this example 4 that I'm proposing. So that 1 would have 2 neighbors, 2 and 5. So if I called DFS in order, I'd hit 2 first, and then I'd hit 5 later. So I called 2, and it seems to handle this case fine. And I can come back and deal with 5 later. Is there an edge case where there could be complications? What if 1, 5, 3? So it's not a greeting card, but there's a V at the top, and then the graphs converge on 3. So maybe like a greeting card with the top open, but the bottom is pinched down, so that the parallel tab would be 1, 5, 3, 4. Now that I'm doing DFS 1, 2, 3, does it create a concern for when I go to 5? And the answer should be no. It's not a concern. As long as I'm caching, the same way that I avoid looping on 1, I will also just short circuit and exit on 3, because that area has already been seen. Okay, so we need a scene map here. I have process node map. I think this is leftover from the last time that I solved it. So this, can this be a set? But this is basically the abstract pattern of a scene map. And we'll be using a hash map or a dictionary in Python. We might be able to get away with a set, which is a little bit of a simpler primitive because it doesn't have a key value pair. It's just a key store. But that's probably splitting hairs. It doesn't change the time complexity or anything like that. So the strategy that I'm proposing then, approach, time complexity, space complexity, improvement. Let's go over this. So the approach is DFS with cache. And the time complexity will be O of n, such that n is the count of nodes. I need to touch every node. Now, what about the count of vertices? So when we're traversing, the performance often depends on not just the count of nodes, but also the vertices. So would 1 have multiple connections to 2? That doesn't seem to make any sense. But one could have a connection to 2, and then a connection to 3, and then a connection to 4, and a connection to 5. And so 1 to 2, 2 to 3, and then also 1 to 3. I would make the traversal, even though I would short circuit from proceeding from 3. But I would make the traversal. So, right, I think this is better expressed as O of V plus E, because I'm going to make those traversals. So it impacts the performance. So this is often called V plus E. So V is the node count. It's the number of vertices. And E is the edge count, or the number of connections. What about the space complexity? I think it's similar. I think it's similar because the product will need to clone not only the vertices, but also the edges. Okay, so can we do this any better? Maybe only in weird ways, I think. So one thing that we could do that could reduce the space complexity is if I cache only the nodes that I've seen and not the vertices and the edges, just the vertices. And then at the end, I loop over the original graph. So now that I've created an output which has all the right nodes but may be missing some connections, I then once over the input and I add all the connections because the destination nodes will exist. So I'll say maybe one weird one. So we could cache only the nodes, not the edges. Then before returning a partial graph, loop over input, and add missing connections. So that would not improve performance, but in theory it would reduce the space complexity. I'll avoid this implementation. So I'm imagining that I'm in an interview situation. I'll avoid this implementation due to time required to implement. But at least we called it out. And then we could also do BFS, but no perf or space gain. So here I'm just demonstrating that I can think through like a few different patterns, and there are other ways to do it. But at this point, I would say to the interviewer, like, what do you think? Can we go ahead with DFS? And I would expect to get a thumbs up. I'm not seeing any questions in the chat so far. Thanks for being here. And if you're enjoying the video so far, consider throwing some likes on it. That helps the algorithm send it around. Okay, so let's dive in. So do I want clone graph to recurse on itself, or do I want to create a helper? I don't see a need for a helper. Okay. So what am I making? I'm making new graph is going to be what? It's going to be a new node. And it's going to have a value and neighbors. So value is node.value. So I already checked if we don't have a node, right? So now we do have a node. Let me indent this. So now we do have a node. And the value is always numeric. It's an integer. It's not nullable. Okay? So I will say that the new graph is this node. And then I need to calculate the neighbors. So the neighbors are none by default. Cool. So I will DFS at that time. Then I'll have the new neighbors. I will set them. And then I can return new graph. I think that's it. So let's do this bit right here. So if node.neighbors So if we have some neighbors, then we need to DFS on each of them. And just say for n. Clone graph is on the solution class, so we'll use self.clonegraph. And I think this is what I intended to do. So this neighbor will go clone downstream of it, and we'll eventually come to a none pointer, which we handle. Or a value pointer with no further neighbors, which we also handle. So I think this should create all of the new nodes and append them in order. Okay, let's step through the an example case. 1, 2, 3, 4. So I come in, I have node 1. We pass this null check. I make a new graph. I get node with 1. And then I say, does the node have any neighbors? It does. It has a singular 2. Okay. So we initialize a new list, and then I find my 2, and I clone the graph of the 2, and I append that to the new neighbors. When I am calling this, I pass in the 2. So before we get here, we are calling clone graph again. And now we're going to dive into the 3. And we're going to dive into the 4. And we're building the call stack on line 38. Before we ever proceed, it grows to a depth of n. And then 4 is going to call to 1. Okay, so I have the infinite loop problem here. Yeah, I have the infinite loop problem in this one. So how do I know I'm going to try to do this with a set instead of this process node map. So what I want to do if not node, I'm not going to set none into my set, but if I pass it, Yeah, I'll immediately check. If node in scene return, what would I return? I want to return up to the appending to preserve the connection. So I want to return I want to return the clone. Okay, so I do need a map, not just a set. We're not just saying, oh, I've seen it, escape. We're saying, oh, I've seen it, give me your clone. So maybe I'll call this like processed clone map. I don't know if that helps at all. But if the node is in the processed clone map, then we'll return the clone. Okay, otherwise, I initialize a new node and my processed clone map of the source node gets a reference to my clone. Maybe I'll call this new clone. Okay, so now in the case where 4 pings 1, I say, oh, I've already processed 1. And so here is the clone number 4, so you can put it in your neighbors. But I'm not going to go through the traversal again downstream, because that would create a loop. So I effectively short circuit, but I provide the copy that I want. So I think this is worth running. Oh, gee whiz, did that fast? Got him. My wife's over here reading some book. She's not impressed. I did it in 19 minutes. She doesn't care at all. Okay. Dub in the chat if you thought that was cool. All right, so I did this in under 20 minutes. So as promised, now I'm going to go wreck myself on course schedule. Okay, great. This is a rough one. Okay.
The tea's bad.
I'll drink it. Do you want to give it to me? Okay. But you don't want to sit up. I made her tea, but she doesn't like it. It's good stuff. I think it tastes like chocolate.
Tastes like an ashtray.
Those are good too. But a chocolatey one, right? Can you all hear her? Count to 3. You're a weirdo. She's throwing shade on my tea, but then she won't count to 3. Okay. I'm similarly going to time box this. I'm actually not confident that I'll be able to knock out course schedule. I'm probably just like manifesting negatively, right? But anyway, we're going to do 20 minutes and then look at the solution. This is not just a thing that I do. This is what I recommend that you do. So that I'll recommend that as you go through the kata, you're practicing 2 problems a day. And that should take you 1 hour a day. Not 7 days a week. I mean, you can do 3 or 5 days a week as you progress. And you'll be able to get through the standard kata, which is a list of 12 problems, within like a month or so. Does that math check out? Typically, that's what happens. Yeah, that math checks out, right? So then you would need to do at least 3 a week. And then a lot of times I'll see people do more than that, because part of the idea of the kata is that you do the same problem multiple times. So yeah, 3 to 5 a week. If you're so inclined, if you're in crunch mode, you can do more. But I think you can get through the standard kata in a month, 3 to 5 a week. And in that hour block, you'll be coding 20 minutes or less. Once you get good, you'll be able to do 2-sum, 3-sum, like well under there. But you kind of time box yourself and then look up the solution. And so then you spend 10 minutes and look up multiple solutions so that you can actually understand what's going on. Don't just take like the first one that you see. So that your coding time block is 20 minutes and your study time block is 30 minutes. And then you get 2 of those study time blocks. So you're looking at 2 problems per session. Does that make sense? Okay. there are a total of num courses that you have to take, labeled from 0 to num courses -1. You're given an array of prerequisites where the prerequisites the I index of prerequisites is A sub I, B sub I. And it indicates that you must take B sub I if you want to take A sub I. Okay, so B sub I is the prerequisite of A. B is the prerequisite of A. Makes sense. Does this mean that there is always one prerequisite of A? No, it means that this is a flat list. So you would have multiple entries. So you could have A sub I, B sub I, then you could have A sub I plus 1, B sub I plus 1. But A sub I plus 1 might take the same value, say 3. So A sub I plus 1 might take the same value as A sub I. Does that make sense? So that's how you'll be able to establish a class that has multiple prerequisites. So we want to somehow consolidate those. So here's a note. Need to somehow consolidate prerequisites. And let me add the word may. May need. There may be some way to do it without consolidating those. Actually, I'm sure there would be. I'm just not sure which is simpler at the moment. Okay. For example, pair 0, 1 indicates that to take course 0, you have to take course 1. Oh, we just want to return the Boolean whether it's possible. Okay. There are other versions of this problem. There's like course schedule 1, 2, 3, and more. And in other versions of the problem, you'll actually need to return the topologically ordered list of courses. Yeah, this is basically a topological sort problem. And I like to do these via BFS because the mental model is easier for me is the reason. Let's see. Is there a better reason than that? That's really the only reason that I like to do these in BFS. BFS topological sort. I think you can do a DFS topological sort. Let's see. Why would that be hard for me to imagine? I think I just put myself in the shoes of the student. And I'm like, okay, can I take that course? No. Let's revisit it later. Can I take that course? No, I'm not ready. Let's revisit it later. And I think that I think that's the reason that the DFS mental model is hard, is because the BFS topological mental model is so intuitive because it reflects the behavior of the student. And it's so intuitive that it's hard for me to like shift into what is the DFS equivalent. Like how am I even traversing the list of prerequisites from a DFS perspective? Okay, so how would this be? So in DFS, to take course 0, you first have to take course 1. So the student, I'm asking the question, can I take 0? Then it causes me to ask the question, can I take 1? And so there will be some list of courses or a set or a hash map of courses that I've already satisfied, I've already taken. And if that returns yes, then currently I can return yes. So I sort of step into one, and then one may have just some dependencies, right? And here we see example 2. This is a cycle, and that would be easier to detect in DFS, because if I note that I'm in the current checking process, so I'm trying to check if I can take course 1. That checking process, I'm stepping through 0, 1, 2. I'm stepping through. And if I revisit a course that's already in the checking process, I've got a loop. And the answer will be false in that case. So that's nice. In DFS, so DFS makes cycle detection easier. So what about BFS? Yeah, I guess this is not true. I guess I need this sort of scene map either way. I need a scene during current iteration data structure to detect cycles. So that's going to be true regardless of DFS or BFS. So I'm trying to work through the DFS mental model. So let's say that I've gotten no loop. Oh, then it's just true. It's just because all we're trying to say is whether it's possible to finish all courses. So if I make it to any terminal condition, then the answer would be true. It's not saying whether, how long it would take or something like this, or in what order. It's just saying that it's logically possible. Yeah, okay, so this is like a cycle detection problem. This form can be done as a cycle detection problem. Much easier MIO than Topo BFS. I'll use DFS because it is my go-to for cycle detection. Okay, so if I go with this approach, do I still need to consolidate prerequisites? So here I am, I'm on 1. I don't know that it's necessary, but it is intuitive to me. So I'll do this. Maybe not necessary, but intuitive to me. Okay, so let's proceed to the algorithm. Well, okay, yeah, let's describe the algorithm and then we'll do time complexity. Okay, so there's basically a 3-phase algorithm. And the time complexity for this, we need to check every course. So it's O of n. At least. It's at least O of n. All right, what about space complexity? Since we're doing DFS, space will be held on the stack. And in the worst case, the stack length is all the courses. If we do have this consolidation structure, then it could be O2n. And then if we have some sort of additional cache, it could be O3n. But it will asymptotically be O of n in any case. Okay, so let's go for this. So I'll call this depths by course ID. And then key is course ID. Val is list of depths. Depth course IDs. For P and prerequisites. This is going to be a 2-length list. And then 0, 1 indicates that to take course 0, you have to first take course 1. So the dependency is the right. So this will be course to take is 0 of P, and then dependency is the first index. So if course to take is in depths by course ID, then we will append to this already existing list. Does that make sense? Otherwise, we need to create the list. No such list exists. Okay. Okay, so now each course is a key, and so if I can get through the keys, I'll be able to return true. So here's to do, get through keys, and then return true if I make it this far. We'll return false if a loop is found. Okay, so for course ID in, so we'll return false if a loop is found. I think in this case, I don't want to call can finish. I'm also noticing that I haven't used num courses at all. So there's definitely a different strategy I could take. Yeah, but I don't know if it's necessary. I think this will be fine. In the topological BFS, if I go all the way through, basically the cycle cases get ignored and they don't get completed. So I can check the length of a completed set and see whether it's equal to num courses, and if so, then I completed all the courses. But I'm not going that direction, so I don't think it matters. So course ID is going to have the cur dependencies. And so the question is, can I complete each of these? And I need my data structure, which is like I've already seen this course on this iteration. Maybe it can be a set, like why not? I think it can probably be a set. So what have I seen so far? I've seen course ID. This feels like a good place for a helper method, because I want to do this kind of DFS logic, but I don't want to call this whole thing. So I'll make a helper. What's the helper going to be called? I don't know. Can finish helper. Not a very good name, but for the sake of expediency, we'll go with this. So if I go this way, then I might not need to do this. What I want to say is, if not, yeah. If I can't finish for this course, then I can't finish for all of them. I don't think it needs to be aware of all the dependencies. It just needs to know the current dependencies. I don't even know if it needs to know all of the current dependencies. I might be able to pass it just one dependency here at a time. I'll do all of them. So we have the current dependencies. We have a new set at the top, but then we'll pass it down through the children, and then the current course ID. Okay, so if, and I have not put the course ID in the set yet. So if the course ID is in the scene, like that's a problem. We're in a loop. Otherwise, we'll add it and say, now I've seen it. Yeah, I think I'm structuring this incorrectly because I think I want the set to go across the siblings. So let's try doing one at a time. Okay, this feels more like the right thing to do. So now I've checked this node, and I just want to check its dependencies, kind of like the second or third step dependencies. Ninad says you got to do DFS. Well, you don't have to. You could do topological BFS if you want, but I am doing DFS, so this can finish helper is a DFS helper. Thanks for being here. Okay, so we're in a loop. Otherwise, we say, hey, this current one, I've seen it. And what about its dependencies? And the pattern should be like this. Like a similar pattern. Okay, so for each dependence, like each, what'd you call this? Like a grandchild dependency? It's like a dependency of dependency. We'll call this second order dep. So for each second order dependency, we pass through current scene, and then this would be updated here. Okay, I think that's what I meant to do. I'm not sure this is well implemented, but that's basically the idea that I had. All right, let's walk through a test case. So example 1, we come in with 1, 0, and then we say, hey, give me that 1, 0 to linked list. The 1 is the course to take, and the 0 is the dependency. Is that right? No, I think that's wrong. Oh, no, that's right. The example talked about up here is different than the, because here it says 0, 1, and here it's 1, 0. To take course 0, you must first take course 1. So here, to take course 1, you must first take course 0. Okay, cool. And then I say, is 1 in my hash map? Like, no, it's not. So I come over here. And now I have a length 1 dictionary. So for course ID in here, so I'm getting the value 1. And then the current dep is going to be 0. If I can't finish 0, then I return false globally. Otherwise, I return true globally, because there's only one iteration here. So that pans out fine. So 0, we haven't already seen 0. We add 0 here. There's no second order dependency. So we return true. So that checks out fine. Let's go to example 2. So example 2, we get done down to here with that 1, 0. So the value of 0, we step in here. This is going to be 0, an empty set, and like, I'm not going to spell out the dictionary, but it has 2 entries in it. And one of those entries is 1, 0, and the other is 0, 1. So then I'm down here. If 0 is in current scene, it's not. So we go through here. And then here, we catch a 1, which we didn't in the other case. So here we say, what about the second order dependencies of 0? Well, the answer is 1. And then we say, well, can we finish 1? And then here we get caught on the 1. Maybe we don't. Maybe we don't. We should, but I don't know that we do. So did I actually insert 1 anywhere? So course ID. So I need to cur scene.add course ID. I think I was missing that. Okay, let's see. Cannot access this thing when it's not associated with a value. Bobby says topo sort. Yeah, that's a possible solution, but I didn't want to do it. So you can do it DFS or BFS. It works both ways. Yeah, you can do it as a topo sort if you want. So how did I write? I like wrote this out wrong. For second order dependency. Oh yeah, I did. I should say current dep. Good. Good. I can change this to a get and then default it to an empty list. I'll probably have the same problem up here, right? Wrong answer, bummer. 45 out of 54. Okay, so let's see what I got wrong. We're basically at the time box anyway, so we'll just look up the solution here. I'll read through one of the ones that I got wrong, and then I'll look through the solution. So 1 and 4, 2 and 4, I collapsed them. And so I collapsed these into a 2-length dictionary. So 4, I need to take 1 and 2. In 3, I need to take 1 and 2. Yeah, I never state that I took 1 and 2. Okay. This is like super wrong. Yeah, my solution's like super wrong. 1, 2, 3, 4. So num courses is 5. Tommy says, who are you talking to? Well, I'm kind of talking to myself. So when you do the, I do have some people on YouTube. I'm multi-streaming to different streams. So we have Bobby and Ninad over there. Thanks for being here, guys. But also, even if no one was here, it's just a good practice to talk out loud as you go through these problems. So the Leetcode kata is an interview prep routine. And during the Leetcode interview, you're going to want to speak to the interviewer to let them know what you're thinking. That's basically what they're monitoring for. If you just kind of go silent mode and you're like typing on your keyboard, but you're not talking with them, big red flag. So you want to be talking with them. And so to help with that, as part of the kata, I recommend that you should say things out loud as you go. So it's a good practice, even if no one was here, even if you are by yourself. Like literally, even if you're by yourself in a basement, like I still recommend that you vocalize what you're thinking. Tommy says, you have an econ PhD. What do you think the Trump policies will do to the economy? I'm curious. So I go with the rest of the market. You can just watch the NASDAQ over time. And you can see that after the election, there was a boost, right? So it's going to be nuanced. You're going to get all sorts of edge cases in particular industries, particular job families. But overall, NASDAQ is going to be tech primarily. So for tech anyway, it's going to be a good thing. Now, outside of tech, I'm less interested in because the main thing that I do is I help people get a tech job, programming specifically. If you look at things like tariffs, these are going to be negative on import goods, but that won't hurt the domestic software engineer job market very much. There's going to be like tariffs are not great, right? Tariffs are inflationary to the overall economy. I don't know if he's actually going to do these things or if they're like a policy, like a negotiating tool, right? So it's speculative to even say that he'll do them. But I will say that for tech specifically, it's looking good. And I'm expecting more jobs in Q1. Good time to grow your software portfolio. Okay, let's look up the solution. So I think I should be making use of this num courses. And I should be saying, like in this case, I should be saying, oh, 1 and 2 don't have any dependencies, so they're already completed. And I basically skipped over that entire consideration. So this is my own solution from a while ago. Let's look at it. And it is a topological BFS. So it's pretty verbose. Yeah, it's pretty verbose. But one of the things that's really nice about this approach is it scales beyond this problem. So the whole class of course schedule style problems, it can solve all of them. So here, this is returning a bool, but what if you actually wanted to return the actual order? You could do that too. So yeah, in hindsight, I should have bit the bullet and just gone for the more verbose approach. So here I do merge the adjacency list, but then I go through BFS. And what do I do with the num nodes here? That's going to be different. Num courses. Where in this logic do I say, for example, course 1 was completed? The input degrees is assumed to be 0. So you're like automatically, yeah, that's how I do it. So this accounts for the logic that I missed where it's like, hey, 1 and 2 were completed because we assume that the dependency count is 0. And then later down here, it's like, hey, if your dependency account is 0, then we're adding it to the queue. And it eventually gets added to the topological in order. Ninad says, last year's job market for tech was bad. What do you think will happen in 2025? So I talked about that a bit. I think it's going to be better. I think 2025 is going to be better. Not like 2020 better. We'll see. That's not what I'm saying though. It might be, but that's not really what I'm predicting. But I think it will be better than this year, significantly better than this year. Tommy, how long have you been coding for? Did you major in CS? I did not major in CS, and I've been coding for 10 years. All right, so we can grab this, and I think it's going to work just fine. So what should we say to an interviewer if we run into this problem in an interview? How do we oh, thanks for the follow, Tommy. Yeah, how do we justify doing a pretty complicated implementation on a relatively simple problem? I want to look for it, and I think it's a pretty good answer is like, I just go for topological BFS for any of these course style problems. I think that's a fine answer. Let's look at this. Yeah, see, this is more concise, right? They want to use a default dict. I like it. I feel like that's a good solution too. Yeah, so maybe the justification is like, it just doesn't add much. Yeah, it doesn't worsen the space complexity. It doesn't worsen the time complexity. It's slightly more complicated, but it's only more complicated by like a few lines. So topo order instead of decrementing num courses is the main difference, and it's really not a big difference, but it gives us a framework that scales to many more kinds of problems. I think that would be a reasonable answer in an interview setting. Hey, thanks everyone for being here. Remember to follow the page. I do these Leetcode problems every week, and then also I'll be doing some